Yes, I will talk about this work about quantum copy protection of compute and compare programs in the quantum random oracle model. And this is joint work with Andrea Coladangelo from UC Berkeley currently, and Alexander Poremba from Caltech. Let me start with an introduction. First of all, I would like to look at some prominent examples, prominent and less prominent examples of quantum advantage in cryptography. So usually, or many times at least, this advantage is actually an all versus nothing advantage, where basically some things are possible in using quantum information processing techniques that are impossible classically. The historically first example is that of quantum money. So this is the idea of using quantum states as bills for a digital money system, and they're kind of the main property of quantum mechanics that is used is the so-called no-cloning theorem. So the idea is that these bills are they cannot be copied, and they cannot be forged by other means, but they cannot be copied by means of the so-called no-cloning theorem. Other examples include quantum key distribution. That's maybe the most prominent example of quantum cryptography, and here also the no-cloning theorem plays a big role, because the idea is that the transmission of quantum states cannot be observed or copied in any way without disturbing it. Other examples include two-party cryptography, for example, coin flipping, or some other two-party cryptography primitives in the bounded or noisy storage model. Then there's things like position verification. That's something that's well known in this audience, at least. Especially well known in this audience. And then there's lesser known primitives like revocable time release encryption. So that's encryption schemes where I can encrypt and then hand you the ciphertext, and it will take you some time to decrypt. And if I ask it back from you before that time has elapsed, then I can kind of verify whether you gave me the right thing back. And if the verification checks out, I can be sure that you don't have any information about the underlying plaintext. That also crucially relies on the no-cloning theorem, right? Because if you were to try this classically, then of course you could both hand it back to me and keep it by just making a copy. And then there's other primitives like unclonable encryption, and finally quantum copy protection. And I marked quantum money, unclonable encryption, and quantum copy protection because they are kind of the ones that most obviously rely on the no-cloning theorem, and therefore on the uncopyability of quantum information. But kind of the reason why I wanted to show you this list is because they all of these primitives, or all of these quantum cryptographic protocols, rely on the no-cloning theorem. Also, for all of these primitives, there are protocols with varying degree of security that rely on these special states called BB84 states. So let me quickly introduce them. So for 2 bits, V and theta, we define the state V superscript theta by using the computational basis state indicated by V, and then applying Hadamard if theta is 1, and otherwise do nothing. So this set of states is fairly well known, I think, and it's just this set. It's 0, 1, plus, and minus. We just for notation, we extend this notation to strings. So if we have V and theta n-bit strings, then we denote V superscript theta just the tensor product of the states indicated by the bits of these 2 strings. So it's like V1 superscript theta 1. It's by this definition we know what that is, and then tensor the next one, etc. So one reason why they are useful in this context is that they have a no cloning theorem. And that can be made quantitative, and that's something that was done by Molina, Vidic, and Waters, at least as far as I know. This is the first theorem of this kind that was proven, and they prove that if we have v and theta n-bit strings, and some algorithm is provided with the corresponding BB84 state, and is supposed to make 2 copies of it and output them as part of registers A and B. And here we add another register E, which is kind of the internal working register of the of this algorithm. Then the success probability of such an algorithm in cloning or copying the state V superscript theta will be severely limited. And so the success probability is measured in terms of this overlap here. But there's still the register E that we need to get rid of. So we just take the 2 norm squared. And then we take the expectation over V and theta, which are chosen uniformly at random, right? And then this expression is actually upper bounded by an exponentially small bound. So 3/4 to the power n. So by just making these BB84 strings or these BB84 states long enough, we can basically suppress any copying attempts exponentially. Let me just quickly, let's quickly have a look at the defining application, which is Wiesner's quantum money scheme. This is kind of, at least as far as I know, the first protocol in kind of quantum information processing that has been ever invented. It works like this. Basically, a bank is outputting these BB84 states as bills. So these are kind of the money states, and they can be passed on between people to pay for stuff. People can send it back to the bank to have them verified, right? The bank will then answer that this bill was valid, but they cannot be copied, as we've just seen. And this is kind of a fundamental requirement for money schemes. There are like several problems with this, and this has been further developed with later. But I just wanted to quickly mention it as the kind of the seminal application of these states. Now, next, I would like to look at unclonable encryption, and that's because our copy protection scheme, as a kind of copy protection, is closely related to unclonable encryption, and our scheme and our security proof, they are both making heavy use of a previous scheme and a previous proof proposed for unclonable encryption. So informally, unclonable encryption was introduced by Gottesman in 2002, and in 2020 it was kind of formalized. There were some formal security definitions put down, and it was studied by Broadbent and Lord. So this is a security property of a private key encryption scheme. So let's have let's just get kind of the syntax of a private key encryption scheme quickly recapped. So here is it consists of 3 algorithms, right? So we have a key generation algorithm that just generates the private key. Then we have an encryption algorithm that encrypts with that private key K, and we have a decryption algorithm. So now let's have a look at the security game that is used to formalize this kind of unclonable security. So it has 4 participants: a challenger, a copier, and 2 decryptors. And it proceeds as follows. First, the copier, just as in indistinguishable security that that some of you might know, the copier first provides the challenger with 2 messages, M0 and M1. Now the challenger samples a random bit B and generates a key K and sends back the encryption sigma of the message MB like, the choice of the ones that the copier provided, but specified by the random bit B with key K. Oh, sorry. And now the copier is supposed to attempt to copy this ciphertext. So here we allow this ciphertext to be a quantum state. And the copier can now use an arbitrary map to produce a bipartite state rho AB. So just an arbitrary quantum channel phi that is applied to sigma. And now the copier provides the two parts of rho, to registers A and B, to the decryptors 1 and 2.
So, Chris?
Yes?
So you said arbitrary, but is it polynomial time or even unbounded? Like, could phi be unbounded?
You can study this in any setting, right? You can study it in the information theoretic setting, in the computational setting. You can think of it as an arbitrary map for now, right? It's supposed to replace int in the classical, in normal encryption, and for int also it's interesting to study in the information theoretic and also in the computational setting. Now the game continues by the challenger providing the key to decryptor 1 and 2. And now their task is to actually decrypt and decide whether M0 or M1 was encrypted. So decryptor 1 outputs a bit B1, and decryptor 2 outputs a bit B2. And now they win if they both guess correctly, right? If B equals B1 equals B2. Any questions about that?
Sorry, I mean, why two decryptor is necessary here? I mean, can we just check if one decryptor win if one decryptor have a correct answer, or should we?
So
okay.
In that case, note that right, one choice for this map here would be to just hand sigma to like store sigma in the register A and hand some dummy state to decryptor B. And now, of course, with sigma at hand, decryptor 1 can just perfectly decrypt.
Yes.
Right. So the whole difficulty of winning this game lies in the fact that they both have to decrypt.
Oh, I see. Okay, thank you.
So now let's have a look at a naive scheme using BB84 states. So here we just, key generation just generates two random strings, R and theta, which are n-bit strings. And now encryption just takes the message, encrypted using the one-time pad encryption, but then encodes the corresponding one-time pad ciphertext in the BB84 states, in the BB84 basis, using the other state, the other string, theta. So now, right, this as an example, maybe I put like some other colors right here, kind of example. This would be then kind of 0 plus minus 1 1, etc. Right? It's like some string of BB84 states. And decryption now just first decodes the BB84 basis and then decrypts the one-time pad and then measures. This only has kind of a weaker security as we have just seen the definition of. And that's, yeah, so kind of a one-wayness style security. And the reason is that somehow this is, you can see that this is kind of a product of encryptions of the bits. So that's not so good in terms of unclonability, because for, say, n equals 2, so the message length equals 2, if the copier uses messages 1 1 and 0 0, asks for an encryption of that, and then just sends one of the bits of the encryption to each of the two decryptors, then they can win perfectly. And that's, of course, that completely breaks this indistinguishable unclonability. So here's an upgraded scheme that works better, and it uses a random oracle. So that's why the title also has the quantum random oracle model in its name. So here we make use of an oracle for a random function from m bits to n bits, and this is usually a model for a cryptographic hash function. So while strictly speaking, we're in fantasy land now, right, where we have access to this oracle for a random function, this is an accepted way of modeling the use of a cryptographic hash function. Here's how it works. Key generation still just outputs two random strings, and encryption actually samples a random string, x, and outputs the BB84 encoding of x together with, again, a one-time padding of the message, but this time with the hash of x. So now this time note that that we here just have a classical one-time pad encryption of m with the hash of x. And to facilitate decryption, we provide x, but encoded in a random BB84 basis. So in some sense, x is also encrypted using the key theta. Oh, sorry. Yes?
M has to be bigger than n, and the message length is n?
Yes. And what I forgot is in the hash, I want to also put the other part of the key, like this. Okay. Decryption works as you, I mean, in a straightforward manner, just by decoding the BB84 encryption and then decrypting the one-time pad. And
sorry to interrupt again, but I guess potential confusion is the use of m here, right? So
yes, I was exactly
some kind of security parameter, and the other is the message.
That is true. That's a bit unfortunate. I'm sorry about that. Yeah. So
but what is the length of the message m? Is that still n?
That's n. Yeah.
Okay.
Right.
But what is m? Is m like 2 times n or so, or something like that?
It could be, for example, 2 times. Yeah. Here, I guess here it's 2 times n. So maybe if we just put 2n here, then kind of the ambiguity is gone. Like this? No, everything is fine.
Yes.
Okay. Sorry about that. That was confusing. Okay. So this should really be indistinguishable and clonable, right? Because now kind of the hash function scrambles the input and kind of breaks this product structure of the ciphertext. And actually, Broadbent and Lord can prove that fact for non-entangled decryptors. Okay, so now let's move on to copy protection. Copy protection is kind of very similar to unclonable encryption, except that we kind of replace information that is contained in the ciphertext by a functionality. So copy protection is really what you think it is, and what people have been trying in different ways in software manufacturers, etc. It's about taking a piece of software or a circuit in theoretical language and encoding it in a way such that it can be evaluated, that it can be even passed on, right? It can be, you can even borrow it to your friend, but you cannot both keep it and borrow it to your friend, right? You cannot copy it. And this concept was introduced by Aaronson in 2009, and with the hope of actually being able to do something like this using quantum the quantum node cloning theorem. So before our work, provable security for copy protection was only achieved using what I would call tailored oracles. So they happen kind of in a theoretical world where everybody has oracle access to some very structured oracle that is tailored to the application, right? And in particular, it's not so clear how to instantiate them. It might be that they are not instantiable. The motivation is obvious. I mean, I kind of gave it already, and it's kind of closely related to the motivation of the task of obfuscation. So let's look at how to define a copy protection scheme. So it has two algorithms: protect and evaluate. So protect takes as an input a circuit C from some circuit class curvy C, and it outputs a quantum state psi. And evaluate takes as input such a quantum state psi and an input string X that's supposed to be like an input to the circuit, and it outputs a string Y. And now correctness is basically, because we're using quantum techniques, we don't want to be too strict, but we would like the following to happen. So first of all, right, if you first protect a circuit C, and then you evaluate using that circuit C on some input X, then what you want to get is C of X, right? But then let's be a bit more large about this, and let's only ask that this happens with, say, 1 minus negligible in some security parameter lambda, but for all X. So for all X, we want that the probability over, the randomness of quantum measurement and the randomness of the protect and evaluate algorithm in general, to the probability to be 1 minus negligible, that this evaluation actually succeeds. Now let's talk about security, and actually security will be defined relative to two distributions. One is the distribution of circuits. So within the class curvy C, we need to have a way of picking a challenge circuit, and I guess the strongest imaginable way would be to let the adversary pick, but what we can prove, and also what all the definitions that have been put forward for now do, is that we fix some distribution from which this circuit is picked at random. And then there's another distribution, which is kind of the distribution of challenge inputs. So in the end, we want to kind of check whether somebody has succeeded at copying. And how do we do that? We check that by challenging them. Give me the output of the program on this and that input. And these inputs also have to be sampled. So here's the security game. And it looks very, very similar to the security game of unclonable encryption, except that now the challenger samples a circuit C from the distribution d lambda and some challenge inputs. Now the challenger sends to the pirate the protected version of the circuit C, right? Now the pirate, and this is, sorry, this is, let's call this sigma again. And now the pirate again can kind of apply an arbitrary map to this phi to produce a state row AB on two registers, and the two registers are sent to the two freeloaders. Now the challenger sends the challenge inputs X1 and X2 to the two freeloaders, and they output two outputs, B1 and B2. And now, in this case, they win if Bi is equal to C of Xi, right? So basically, if they both succeeded in computing the output of the circuit C on the challenge inputs. Okay, let's have a short thinking break. Are there any questions about this? Okay, if not, then let's move on to our results. So in some sense, I mean, this definition is very close to, that's something I should mention. This is very close to the definition that was put forward by Aaronson in the original paper about copy protection, but it has some small changes to it. So in our work, what we do is we construct a copy protection scheme for point functions and eventually for compute and compare programs, and prove their security. So point functions are just functions that are 0 except on one marked input, which we call y here, where it outputs 1. And for simplicity in the following, we will just think of the protect algorithm actually taking input y instead of a circuit for py. So what are compute and compare programs? I want to quickly mention this. In the rest of the talk, I will focus on point functions, but compute and compare programs are kind of slightly more expressive generalizations of point functions, where basically first a function is computed and then the output is input into a point function. So the compute and compare program defined by a function f and a point y, evaluated on x, outputs 1 if f of x is y, and 0 else. And you know, as you can see, kind of this compute and compare program implements a function that's just the composition of a function f and a point function y. And it turns out that for copy protection, as opposed to obfuscation, for example, it's sufficient to copy protect the point function and to send the function f in the clear. There are some wrinkles to that, and you need to make sure that the output of f still has kind of sufficient entropy when you map, when you draw it from the distribution that's used to define security. But that's kind of a natural generalization of a requirement that also holds for the point function case. Okay, now let's first look at a naive scheme again. So how do we do this? The protect algorithm now just samples a random string z, and it outputs z encoded in the BB84 bases specified by the marked input y of the point function, right? Note that we are at this point, you know, we are copy protection. We copy protecting the point function py, right? And now evaluate will just, you know, it gets as input a copy protected program and an input x. So now it first applies Hadamard according to the string x to the state psi, measures it, and say the outcome is z hat. Now it outputs 1 if z hat equals z and 0 else. So why does this work, right? In some sense, it works in some sense because we encode it using the marked input, right? So if x is equal to the marked input, then we actually obtain the outcome z with certainty. But if this input is not the marked input, then this measurement will actually be performed in some misaligned basis. So we could get a random outcome. And you know, this will at least not happen with probability 1. But the problem is here it starts with correctness already, because correctness only holds in a very weak sense. Because if we take some x and y and they have Hamming distance d, then if we first protect the point function with marked point y and then evaluate at x, then this success probability here, the correctness probability here, is actually 2 to the minus d, right? Because there's only d positions at which the the BB84 basis is misaligned. So in particular, if that distance is 1, then with probability 1/2, the evaluation fails. And note that somehow correctness is here extremely important, because one thing that I didn't talk about is that where was the definition? We defined the evaluation to just output the output, right? Where was that? Here. Here, in the definition of evaluate, we defined the output to just be the output string. That's kind of less than desirable, right? Because we kind of want to keep the copy protected program as well. But note that if this output is deterministic, then we can just rewind the quantum circuit that has produced it and recover psi as well. But if that output would be randomized, then that would not be possible. So correctness somehow here also is important for the reusability of the copy protected program. Okay, so let's make a second test.
So is this the only problem on this scheme? Because you could use the error correcting code, right?
You could use an error correcting code, that's right. And that's actually, I mean, maybe out of laziness or something, we are not using an error correcting code, but we are just using an expanding random function. And that's actually the second attempt. Here we just, to choose the basis, instead of using the marked input directly, we just apply a random oracle to it. Instead, we could also apply an error correcting code, I guess. But we use a random oracle that has that's expanding. So the output M is much larger than input. Say for example, 4n. It's 4n. And then we use G of Y for the mark point Y as the BB84 basis in the naive scheme. So now for any two inputs to
but that probably is the same thing as an error correcting code, no, Chris?
Yeah, I mean, basically we are using the property that such a random function with high probability is an error correcting code. Yeah, that's right. The point is, this is not the only point where we will use a random oracle. So somehow it was, conceptually speaking, free to just use another one.
If it was, then you would be able to get rid of it.
Right. If this was the only one, then we would be able to get rid of it, but it's not the only one. So we just decided to keep it. Okay, so that's great. Because it has correctness. And it's also not clear. I mean, we don't have an attack against this scheme, but we can also not prove anything about it. So that's of course sad. So let's change the scheme a little bit more to kind of be able to prove something about it. This is now our actual copy protection scheme for point functions. So here we introduce one more oracle. So the previous oracle we called G, and now we have another oracle H that now maps from m bits to n bits. And now the protect algorithm with input Y now works as follows. First, we sample a random string of n bits, and then we output, as before, this random string encoded in the BB84 basis specified by G of Y. But now, instead of providing Z, we actually provide the hash of Z. So actually, we're kind of hiding Z, right? We kind of hide Z, but in a recognizable way. And now, how does evaluation work? It does the coherent version of the following. So, right, this again is that we want to do it coherently. It's just for reusability of the copy protected program. But for simplicity, you can forget about this and just think about the actual procedure that's specified here. So first of all, we apply h of g of x. So x is the input to the evaluation. So we apply h of g of x to the quantum state part of the copy protected program. We get an outcome z hat. And now we output 1 if h of z hat is equal to t, which is the classical part of the copy protected program, and 0 else. So the only change compared so the only two changes to compared to the naive scheme is that, first of all, we use this kind of error corrected version of the or error correction code encoded version of the marked inputs as BB84 basis, and we hide the the random string that's encrypted in this BB84 basis using the second hash function h.
Chris?
Yes?
So this use of hash function h is sort of the same idea as for the unclonable encryption, right?
Yes. Yes.
And well, already back there, I was sort of wondering, is it really necessary to use a random oracle? Because there it seemed like you could also just do a privacy amplification. So you could use an extractor.
Okay. Let me have you ask the question again when you see how the function h is used in the proof.
Okay, sure.
Okay.
Can you say this again, Chris? So I mean, I'm slow, if it's okay. So you measure in this basis, and you get this outcome z hat, and
Yes.
then what do you do?
Now you compare z hat. Now you map z hat through the hash function h. So then you obtain h of z hat, and now you compare that to the classical part of the copy protected program, right? Remember the protect algorithm outputs this quantum state and the hash of z.
So you compare it to the actual hash of z that you have stored as well.
Yes.
Got it. And one question about this coherently. So if you were to do this coherently, then if you actually have the correct value z, then you will get a 1 with certainty.
Yes.
And then you wouldn't destroy the state, but actually you can copy well because you know what the z is.
Yes.
But if it's not, then you say with high probability you will get 0, or you will get something that's not z.
Exactly, and that's basically.
If you were to reverse this, then would you get back the unaffected thing with high probability still?
Right.
Is that the idea?
Yeah. So right, g of x and like the Hamming distance of g of x and g of y, this is kind of large, right? It's like
because of the error correction part.
Yeah, polynomial in n.
Right.
And therefore, like the probability of obtaining 1 in the coherent version of this kind of evaluation procedure is exponentially small. And then by this gentle measurement lemma, or almost as good as new lemma, you kind of can just uncompute and get back your input state.
And then you don't disturb the state at all?
Yeah, I mean,
right?
You disturb it with an exponentially small amount.
Okay, you always do that. Okay.
Yeah. So basically, evaluation can be repeated a polynomial number of times easily.
Yes.
Okay.
Thanks.
Okay, so now let's have a look at what we can prove about it. And this might be slightly underwhelming. It's also underwhelming to us, but I will describe to you afterwards why it still, I think, is a significant advance. That's the following. So if we have a distribution of marked points for point functions where the marked point has some min entropy, polynomial min entropy in a security parameter lambda. And let this parameter m, kind of the error correction parameter, be quite large. So m larger or equal 5n, or larger than 5n. Then there exists a delta, some constant delta larger than 0, such that for all adversaries against the copy protection scheme pi described above, this adversary succeeds in the copy protection game with at most probability 1 minus delta plus negligible in lambda. And this delta, it's a kind of a universal constant for at least for our proof, and that's 10 to the minus 4. That's at least one thing that that works. So this is very weak security, right? So we say, fine, the adversary can actually copy, except that it fails with probability delta, which is small, right? So of course, what we would like some exponentially small advantage here. So note that if we go back to the copy protection game, depending on that input, that distribution of challenges, and depending, for example, also on the output length of C, you know, even if you know, like if the pirate doesn't send anything at all, freeloaders 1 and 2 might have some guessing probability, some non-negligible probability of guessing the output correctly. But we, in some other, like in a properly secure scheme, we would have to compare the adversarial success here with that best guessing probability, and we would like the advantage to be negligible instead of constant. However, this is kind of an improvement over previous things because of the fact that our setting is more realistic, right? Because we can prove this in the quantum random oracle model. Right, maybe we can add this somewhere here, right? This is in the QROM, the quantum random oracle model. Because we can just think of these random oracles actually being instantiated using hash functions. And then in the quantum random oracle model, we can prove this. And this is kind of an established cryptographic security model. Whereas all the previous schemes and constructions were either just heuristic, so that with no security proof at all, or they were in kind of specialized oracular worlds, where instantiation is completely unclear, essentially. Okay, let me use the last 10 or 15 minutes to give you some ideas about the security proof. So similar to Broadbent and Lord's unclonable encryption scheme, what we do is we reduce security of the scheme to so-called monogamy of entanglement games. So what is that? This is a kind of game that was introduced by Thomas Michelfehr and Kaniewski and Wiesner in 2013. And it's kind of a way to gamify the unclonability or the no cloning property of BB84 states. So it proceeds as follows. A copier gets a random BB84 state as input. Then it's supposed to copy it, right? Right. It can, again, we can imagine it applying some map phi, of this v theta to generate registers A and B, which are then passed on to players 1 and 2. And now 1 and 2 both obtain the BB84 bases, theta, and they have to guess the the underlying string V. So they output V1 and V2. They win if V equals V1 equals V2. And what Thomas Michelfehr, Kaniewski, and Wiesner were able to prove is that the success probability in this game is in general bounded by 1/2 plus 1/2 root 2 to the power of n. So in fact, in the length of the BB84 state, n here, so there you have an exponentially small success probability. So if we can now take a successful adversary against our copy protection scheme and from it construct an adversary against this, or an algorithm, a set of players that wins this monogamy of entanglement game, then we're good. And how to do this, there a crucial technique is what's sometimes called pre-image awareness. Classically, in the classical random oracle model, this is a very, very simple technique. And essentially it boils down to if you're trying to distinguish two things and you don't look in the right place where they're actually different, you just don't see the difference, right? It's a very simple thing, and classically it's really not much more than that. So if you have two functions, f0 and f1, and they actually agree everywhere except on some special input x0, then you know, if some algorithm A is provided with a function fb, so a choice between f0 and f1 specified by a bit b, and tries to guess this bit b while this b is chosen at random, then the success probability is smaller or equal than 1/2 plus 1/2 times the probability that a fb queries fb on x0, right? This is extremely intuitive, and somehow it should be obvious. You can otherwise think of an adversary that doesn't query x0, right? It literally behaves exactly the same whether it has function fb, f0 or f1, and therefore it can only have success probability 1/2. Okay. What this enables us to do is to construct a so-called extractor. And an extractor, it's supposed to extract this marked input or the special input x0. How does it work? It just runs, you know, a of f1 or a with oracle f0, and just outputs a random query input. And this succeeds with probability, you know, 1/q times the probability that a actually queries that input. So it's directly functionally related to the success probability of this distinguishing adversary. So in some sense, this is kind of a search to decision reduction. So here's the formula. The success probability of the extractor is larger or equal than 1 over the number of queries that A makes times a function of the success probability of the distinguisher. Okay. Now, what you can also do classically is you can do this in a simultaneous way. So if you have two adversaries, A1 and A2, they're both query algorithms with shared randomness, say. And now you can construct, as just described, two extractors, E1 and E2. Say A1 and A2, they're trying to solve the same distinguishing task. So, but they're both provided with oracles FB, and they are both supposed to guess the bit B. Now you can construct the two extractors. It turns out that they, the probability that they succeed simultaneously is lower bounded by, you know, 1/q squared times the probability that A1 and A2 both query x0, just by the construction of the extractors. Now we can use a union bound to kind of separate this probability here. Right, this is larger or equal than the same prefactor times the probability that A queries x0 plus the probability that A2 queries x0 minus 1. And now we can just apply this this inequality over here to obtain a bound that relates the simultaneous success probability of the two extractors to the success probabilities of the two distinguishers. So that's great, except that we can't do it quantumly. And the reason is that quantumly, let's look back at what we did. So here we have this statement: A1 and A2 query X0. This is just nothing we can talk about in the quantum setting, right? It's in the quantum setting, A1 and A2, they are making superposition queries, so we cannot. It's not an event whether they query X0 or not. There's no transcript of queries that we can just look up whether X0 was queried. So instead, what people do is, at least in the single algorithm setting, is the so-called O2H lemma. And the O2H lemma works as follows. Here, if an algorithm A makes 2 Q quantum queries, then we can construct an extractor that just samples a random number between 1 and Q, and then it runs A until before the Lth query, L being that random number, and measures A's input register. And what Unruh proved about this extractor algorithm is that it succeeds with probability 1 over Q squared times actually this should be the distinguishing advantage. So 2 times that minus 1, I guess. So here again, we have like the success probability of the extractor related to the distinguishing advantage of the decision algorithm. But now we cannot do the same trick for the simultaneous version because there's no transcript of queries, so we really cannot use this union bound argument, right? Note that here, if we wanted to use a union bound, we would need to use a union bound on these probabilities here, and they are suppressed with 1 over Q squared. So there's no, I mean, you get a trivial bound. So Broadbent and Lord actually proved a simultaneous O2H style lemma. And here we have 2 algorithms that both, instead of deciding, actually need to guess the marked input. So right here, they get an input, which is kind of a shared randomness or a shared input that might depend on some number z, some string z. And now, 1 second. We have again this random oracle, and here we have a bit b that gets sampled, and this decides whether the random oracle at some marked point x0 is equal to z, which is part of the input in some encoded way, or independently random. And the success of this this game here is kind of if y1 and y2 are actually equal to h of x0. Somehow the difference to the O2H setting is that instead of just deciding what B is, the algorithms have to actually output the output of the hash function at the mark point. At this, and they were able to prove a bound for this, except that somehow instead of getting the relating it to the advantage of the original algorithm, right here we have kind of the success probability of the original algorithm, which is kind of y1 equals y2 equals h of x0. And then we subtract some function of the advantage. But note that the advantage, the trivial success probability is 2 to the minus n. And what gets subtracted here is 9 times the advantage. And this factor of 9 here is what is kind of a non-tightness. And this is a big problem because if we had a decision version of this, then we would have 1/2 instead of 2 to the minus n. So the factor of 9 just kills the bound. This is basically the problem that we had to solve, and we solved it by proving an additional search to decision reduction that uses the gentle measurement lemma. So if some algorithms succeed with a high probability, we can also apply it to distinguish several oracles, and therefore basically suppressing the success probability that's achievable using guessing, and suppressing it enough so that the factor of 9 doesn't kill us anymore, and that's how we were able to eventually derive a non-trivial bound. Let me skip ahead across the last couple of slides and just pose some open problems. And one of the main open problems that's already inherited from Broadbent and Lord is the 9 in the simultaneous O2H lemma, is it an artifact or is it actually a real factor? If it is real, then we would not, of course, need to find an algorithm that exploits it. And if it is not real, which is what we suspect, then we should find a stronger version of the simultaneous O2H lemma. And closely related is, of course, the problem that we would like to boost the security of the copy protection scheme to a negligible advantage. And first of all, we have some ongoing project of that has just started. But then one way of solving this second problem would be to solve the first problem. Thanks. That was all I wanted to say.